All right, children, ask away. Everything is fair game since the last exam. So reduction, set stuff, is spread.
What's the Cartesian product again?
I'm sorry?
What's the Cartesian product?
If you have two sets x and y, then x cross y, this is called a Cartesian product. It's just a set of ordered pairs. X, comma, y, such that x is in x, y is in y. If I have a whole bunch of them, Cartesian products say like so, n from 1 to capital N of sets A sub n, this would be A1 cross A2 and so on. These would be the n here. This would be the ordered n products. So you form ordered pairs, ordered triples, or ordered quadruplets, whatever you want. Happy? Yes.
So big X and big Y are
The sets.
are sets.
Yes. Next question. Yes.
Wait, so, like, what, you said like strong reduction is gonna be on
Sure.
there, so like, what's sort of like strong reduction?
I gave you guys two examples. One is the proof that every number can be expressed as a product of primes, or prime itself. And then I showed you that Fibonacci numbers have a certain closed form. Those are the two things we did, and it wouldn't be fair to give you anything but something very, very close to those two problems. I wouldn't give you anything very wild. Which one do you want to see?
Fibonacci.
Right. So, here's the proposition. The n Fibonacci number looks like this: 1 over root 2 times alpha to the n minus beta to the n, where alpha is 1 plus root 5 over 2, and beta is 1 minus root 5 over 2. Okay? That's what it says. And here we're given that f0 and f1 are both equal to 1, and generally fn plus 1 is fn plus fn minus 1. This defines, so the sequence fn, n from 0 to infinity, is the sequence or the set of Fibonacci numbers. There it is. Okay, that's theorem. So notice in this case, an observation here. Is that alpha squared here is in fact alpha plus 1, and beta squared is in fact beta plus 1. The reason is that if I solve here, if I take x squared minus x minus 1 is 0, it implies that x is equal to 1 plus or minus radical 1 minus 4 times minus 1 over 2 by the quadratic formula. Which is in fact 1 plus or minus root 5 over 2. There are my alpha and beta. Okay? This, of course, is the same thing as saying that x squared equals x plus 1. Happy? So this fact is going to be used in the proof. Okay, and now, yes,
Sorry, can you just explain the like x squared minus x line? Just that whole where did that?
well, I have this alpha and beta over here, right? And I want to prove that these relationships, in fact, it looks sort of mysterious, but it isn't if you explain it through natural numbers at all. Because you know, in fact, this is a separate observation, the limit as n goes to infinity of the n plus first Fibonacci number over the nth Fibonacci number is in fact 1 plus root 5 over 2. This is in fact my alpha. And to prove this, you end up with this polynomial in the game. Okay? Now, yes,
Is that the golden ratio?
of course it is.
Yeah.
So in this situation here, I get that this polynomial has these two numbers as roots because that's what the quadratic formula gives me. So, because this polynomial being 0 implies this, that implies these two facts. Have I answered your question? Because this is the case, and here I get alpha and beta out, that must hold for alpha and beta, and that's what I have. Now then, here comes the proof. For n equals 1, f sub 1 is 1, and 1 over root 2 times alpha minus beta, first power, this is 1 over root 2. Alpha is this is 1/2 plus root 5 over 2, and beta, I think this is a plus, isn't it? This is a, no, I'm right. This is 1/2 minus root 5 over 2. This should be 1 over root 5, I think. Over root 5. I'm so used to writing root 2 these days, so there you are. And this over here simplifies to radical 5, and there's my 1. Okay? So I've established the base case. By the way, in my mind, typically 5s become 2s and 2s become 5s, so my mistake is not surprising. It's a weird quirk that I have. This company is others. Are we happy so far? How many points do you have now? I have 20. If you wish. 5. The work is still to be done over here, okay? What's the next word? So now here comes strong induction. So suppose that for all L between 1 and K, you get that f sub L is in fact 1 over root 5 times alpha to the L minus beta to the L. For all of these guys. Okay? So far so good? Everybody? Now with strong induction, as with all induction, both induction types, this is the tool you're going to use to hit the next and definitive maneuver. Now we're going to look at f sub k plus 1. Okay. Now this is what we haven't even begun to use it right there. So f sub k plus 1 is by what's given to you, fk plus fk minus 1. Okay? Now, these numbers are both in the given range. So by the induction hypothesis, by this up here, I can take L to be first K and then K minus 1. In weak induction, all I have is the kth case. Now I have all the cases up to K and including K. So I get in here. For this first guy, I get 1 over root 5 times alpha to the k minus beta to the k. The other thing is 1 over root 5 times alpha to the k minus 1 minus beta to the k minus 1. Are we okay so far? People, my Utes. Do you guys know the movie My Cousin Vinny?
Yes.
You Utes. You have this now? Yes, sir.
Why? I'm just. Where did the L come from? Is that
It's just a notational thing. I mean, this says that for all indices 1, 2, 3, 4, 5, up to and including k.
is it an integer then?
Oh, yeah. I mean, for all L, yeah, in Z, for all integers. Natural numbers between 1 and 3. Yes. Okay. So the indices that I'm allowed to accept, that I'm supposed to assume things for. So I get here then, by rearranging, 1 over root 5 in front. I get here alpha to the L, alpha to the k rather, plus alpha to the k minus 1, minus, then I get here beta to the k, plus beta to the k minus 1. Just by beta arithmetic. Yes? You're okay with that?
What does that say right there under the equal sign, under the line above?
What do you think it says?
Enough.
How about induction hypothesis?
Got it.
So,
That was so cool.
now I factor out alpha to the k minus 1 here. I'm left with alpha to the k, alpha plus 1. Second case, I factor out beta to the k minus 1. I'm left with beta plus 1. Okay, Connor, happy? What are you eating? I'm going to kill you. It's on campus food, or is it your own?
Oh, it's campus, yeah.
No, man.
I hope
Russian roulette, I'll tell you.
I hope they kill you.
I told you that story, didn't I, about the old name for food services? Okay, let me finish this book, I'll have this. So, over here, look at that. Circle. So now, this guy here is in fact alpha squared, this is beta squared. So what do I have with? 1 over root 5. I got alpha to the k minus 1 times alpha squared is in fact alpha to the k plus 1. And here, this becomes beta to the k plus 1. And that's precisely what I need, and I just won the game. Okay. Are we happy? Okay, so now, years ago, what is now the layer was split into a smaller version of the layer and placed right next door to the left called the terrace room. That's in Foley Terrace, or whatever. But the students called it the tear-ass room. Because in that place, you would be served meals if you were on a student meal plan. And so you could buy a meal plan and eat 2 meals a day for 6-7 days a week. But these meals were so bad that you would eat the meal and you'd have to run back to your dorm room tearing ass because of the experience that would induce in you. So this is the universal phrase, let's go to the tear ass room and take our chances. So there you have it. How did I come with that? How did that come up? Oh, Connor's food. Yeah. So Connor, if you're an out, I'll understand. Are we okay? Next question, yes.
Wait, can you?
Induction hypothesis.
No, got it. Can you explain kind of like the algebra that you did to change the alpha k plus alpha to the k minus 1 into the alpha k minus 1
Look at the
times?
circle. Alpha plus 1 equals alpha squared.
Oh, okay.
So I factor out alpha to the k. In this case here. k minus one. And so this here, this is of course just k minus one plus one. So if I factor that out, I'm left with an alpha to the first power there.
Okay, yeah, I got it.
And then everything falls out, okay? Next question. You happy? Green Bay won on the weekend. Great game. In the snow. They won by 8 points. Yes, sir.
Problem 9 on
I have,
the.
I don't know, I don't know, just tell me the problem.
Oh yeah. Okay, so let P. Here, can I just give you it instead, or
Number 9?
yeah?
Oh, yeah. You were not here that particular day, were you?
No,
Here we go. We'll do it again, I know.
sorry.
We have A bar and B bar element ZP cross. Right? Show that A bar X equals B bar is solvable. Shut up when I'm working. Because they know I'm working. So, on the exam, I'm not going to give you this kind of jargon. It's not necessary to do so, but the book does it because it wants you to learn about equivalence classes and so on, congruence classes. Here's how this translates, right? ZP cross is written, the book writes it this way, of course, 1, 2, up to P minus 1 like so. This just means the non-zero integers modulo P. And we work multiplicatively, so working multiplicatively. That's all this means. So here, this means, the meaning is this. This over here, ZP cross here, really, you can think of this as all the numbers say A in the integers such that P does not divide A, and we reduce mod P. Meaning, of course, that A, well, you can think of these, in fact, as all the residues, as I say, like so. Or. So this says that you will solve AX congruent to B mod P, given the fact that P does not divide A. So we're going to solve this. You with me so far, everybody? So that's the key to this problem.
Okay.
Now here's a huge situation. In the previous problem, here's strong induction, which is done by turning the crank. And it all came down to this fact being used strategically. Okay, I keep telling you guys, in proofs, in doing proofs, there are very few hardcore kernel ideas. Those ones you identify, the rest is as it were window dressing, but it has to be done correctly. But the idea is what's at the heart of the whole thing, right? Likewise, in this case, this implies the following. The GCD of A and P equals what? What does it equal? 1. 1, absolutely. Because the GCD must divide A as well as P. To divide P, you're 1 or P. But you're not P because you don't divide A, therefore you must be 1. Okay? And now here we go. This implies, by Euclid, there exist integers x, why not? X and y in the integers such that, I'm going to call them something else. X, I'm going to call them u and v. Such that AU plus PV equals 1. Right? Know the Euclidean algorithm better than your own name for the exam. Right? I love this algorithm with a passion. It's very important. The proof is very beautiful. I enjoy it a great deal. When I grade exams, I want to enjoy myself. Can it be any more explicit? No. I can, but I'm not going to be. This is pretty damn explicit. Know that theorem. Okay. Ooh. Very, very disturbing. What happened there? Was it me?
A little bit.
It's a force field. Is your equipment okay?
Huh?
Is your equipment okay?
Yeah, it's fine.
Oh,
It's just a loud noise.
poltergeist. Meanwhile, back in the ranch. Over here. Now, here's a bit of algebra. Watch. I have this situation here. I have AX is congruent to B modulo P. If and only if, now in this case here, well, this certainly implies for this with it. A times U times X is congruent to B times U modulo P. This is the doodle, by the way. Over here. This auxiliary expression over here, like that. I have here that this A times U over here. From here, what does this imply? This says that AU is congruent to 1 mod P. Correct? Because I can cast out multiples of P. So therefore, this becomes 1. So I get therefore that X is congruent to B times U mod P. There is a solution. So now we prove it this way. Here's the proof. Okay. P does not divide A implies that there exists U and V in the integers such that AU plus PV equals 1, which implies that AU is congruent to 1 mod P, which implies that AUB is congruent to 1 mod, to B, sorry, mod P. So, if X is in fact U times B, then we have a solution to AX congruent to B. Namely that one. This one here. B or E the other way. There it is. Okay? Yes.
Why is it I thought we were showing it. If AU is 1, why is it?
AU is going to be 1, but I'm interested in this. AX is B. U is the solution to AX equals 1. UB is the solution to AX equals B.
So repeat that?
Okay. This over here says that U is a solution to AU equals 1.
Mhm.
But I want AX equaling B. B, not 1. So to multiply through by B, I get that this solution is this. It's like saying the following. You know, 3 times a third equals 1. I want to solve 3x equals 5. Then I get 3 times a third times 5 is 1 times 5. Okay? That means that in this case, 5/3 solves that equation. That's what I'm doing. Yes.
And then like for the terminology, for that AU.
The chronology?
Terminology.
Terminology.
Okay. Yeah, for the AU congruent to 1, that's basically saying that A is invertible in modular.
Precisely.
Yeah.
Precisely. Which comes from here, that A is in here. Good. You got it. Next question. Yes.
Could you like do the Euclid theorem again?
I'll do it for you, but I gotta hand it. All right. The point being, handouts are there for you. There you go. What?
We just know you like doing it so much.
Oh, I'd rather have lunch. It's very kind of you to give me such pleasure doing this. Here, let's use these machines around. Oh, forcefully. Okay, so
Bless you.
let A and B be integers. In fact, for fun, let it just be natural numbers. Easy. Then there exist integers x and y. We're going to call them x0 and y0 to be consistent with my notes, such that the GCD of A and B is equal to AX0 plus BY0. So in the application over there, x naught and y naught are u and v. Okay, you got it? That's the theorem. Here's the proof. Let S be the set of all things of this form. So x and y here are integers. And I want ax plus by to be a positive number. So a natural number, in other words. Got it? All right. Now, notice that a is not 0. That implies that plus or minus a is positive, one of them. So either a is positive or minus a is positive. That implies that either a is in S or minus a is in S. Because this is of the form a times 1 plus 0. This is a times minus 1 plus 0, so they're in S. Either one of these. One is positive. Is this clear? That implies that S is not empty. So, S is a non-empty subset of the natural numbers. Which implies S has a minimum. I'm going to call it D. This is minimum of S. And because it's in S, it looks like this. AX naught plus BY naught. Why not? Or some numbers x0 and y0 in the integers. All right? So far, so good? I'm not going to prove that D is in fact the GCD of A and B.
Last time you said that If there was an E that also satisfied, and E is.
That's the next one.
No, but E is less than D?
Yes, because D is the greatest common divisor.
Yeah, but then, so if D is the minimum.
Of the set. E is not in the set.
Yeah, exactly.
Alright. So, claim here is that V is in fact the GCD of A and B. Meaning, in the first place, D divides A and D divides B. In the second place, if E is a positive
Bless you.
in the natural numbers therefore, and E divides A, E divides B, then E is less than or equal to D. So I have to prove these two things. Okay? Happy so far? That's the definition of greatest common divisor. This says D is a common divisor. The second part says that D is the greatest common divisor. Yes?
So if E is, if 0 is greater than
Oh, sorry.
E.
I get rid of these markers. Cursed. Okay. All right. So, here's the proof of one. All right. First of all, the division algorithm implies that I can write A as QA times D plus RA, QA an integer, and RA at most equal to D minus 1. We okay so far? That's just the division algorithm in action. Divide by D, get a remainder, and a quotient QA. Okay. But this equals then QA, and for D I plug in this A x naught plus by naught plus RA. So from here, this number RA, solving for that, becomes in fact 1 minus Q x naught times A plus minus QA y naught times B. This is just algebra. This is the 9th grade. There's nothing going on here, very subtlety. Now, if RA is not equal to 0, all right, then RA in fact is bigger than 0, and RA is in fact in S, because these guys are both integers. This is in Z, this guy's in Z. It's in this form. Okay? So far so good, yes or no? Happy? Okay. But then, if you're in S, okay, that means you're bigger than or equal to the smallest element of S. But then RA is bigger than or equal to min S, which is D. However, RA is less than or equal to D minus 1. From here, it's a remainder. What do we have? An impossibility, right? This is a contradiction. Therefore, RA equals 0. Okay? Because if RA is in this range, if If A is not zero, then a contradiction, therefore A has to equal zero. Okay, you got it, everybody? But then, A is going to be this QAD plus zero, which implies that D divides A. In the same way, prove that D divides B. That takes care of one. Okay? Yes?
Is that for us, or is that a legitimate way to just prove D, or D divides B? Is that like a legitimate way to prove it?
Would I do it otherwise?
Or is that like one of those things like, we should do that later on the test, like we have to go through B?
In the handout, I did both of them for you. If you write this down in the exam, you better be damn sure that I believe you, that you can do it.
Yeah, right.
Ask if I'm that cynical. The wise student doesn't take any chances. Okay. In fact, all kidding aside, this calculation is the heart of the first part. So for you, if you understand this on your own over lunch, do the second part. It works very much the same way, same argument, except in this case, the coefficients are going to be differently situated. But you're still going to have the same argument exactly. And so this tells me, therefore, that I have a common divisor. Okay? Secondly, so for part 2, if E divides A and E divides B, then E divides AX naught plus BY naught, which is D. They're all positive numbers. This implies that E divides D here, so this implies that E can't be any bigger than D. And that does it. That's the whole proof. Okay? Satisfied? Next question. Yes, Connor.
So like, you brought up the axiom of choice.
Oh, yes.
And its importance.
Hugely important.
It seems to underline to these things, but it didn't seem like explicitly stated.
And this does not apply at all.
No, okay, right?
The axiom of choice only applies in the fundamental theorem of recursion. Because I have this collection of classes, many of which coincide. And from those sets, I take one representative of each case. So I'm not going to ask you to do that. That's just too subtle. And like I say, in the handout that I gave you on that, I wrote you the last proof very carefully for you, but that's very deep. And there's so much hiding in the shadows that it's so unusual, I don't think it's fair to test you on that.
So like,
The axiom of choice is very important.
is it not underlying in that minimum of S? Because if that S did not.
No, you're hitting something else there. The axiom of choice says, if you have a set of sets, or a collection of sets, then there's a function that picks one element from each collection of sets. What this says is, ultimately, this is the axiom of induction. It says that a non-empty set of natural numbers is a small cell. That's all it says. But that's a deep principle, but it's not the axiom of choice. It's called the well-ordering principle. It says that a set of naturals, it's not empty, has a small cell.
And then, like you're saying, that's implicitly like induction, because that one thing we did, like non-interesting numbers, then there'd be a minimum non-interesting.
Does it make sense to everybody? Next question. We have time for 10 minutes left to go. Let's go. It's your show. The usual story, 5 questions. Nothing unfamiliar. Okay. Can you prove there's an infinite number of primes?
Yes.
This second exam is going to be rather predictable because I haven't done many different things, but they've been pretty deep things. So know your modular arithmetic, know how to prove certain things about congruence modulo n. Know equivalence classes. Yes,
For the proof that goes A's congruent, if A's congruent to B mod n, A prime's congruent to B prime mod n, then A plus A prime is congruent to B plus B prime mod n. Is that something that we're supposed to use, like apply to another proof, or is that just another proof we're supposed to know by itself?
yes and no. You are certainly supposed to know the proof. In fact, the answer to the question is always yes, except for the axiom choice business. If I prove something like that, you should know the proof, that's critical. But you use it again and again and again. For instance, the partner to that says that if A is congruent to B, and A prime to B prime, then A times A prime is equal to B times B prime, right?
Right.
Let's see what happens. Over here, for instance, look. I start with this, and I go here. I'm using that very fact.
Oh, okay.
B is congruent to itself, so I multiply this times B and that times B, and I retain the congruence. So that is an application of that particular theorem. So once those things are established, they'll be used again and again and again and again.
Okay.
Okay? Have I answered your question?
Yeah. Is it possible to go over that proof?
Sure. If A congruent to B, mod n, shall we say, and A prime congruent to B prime, mod n. And I'll give you, there are two ways to do this. Here's the easiest one. This implies, in particular, that A minus B is n times some q for some integer q. Right? It also implies that A prime minus B prime is n times some q prime for some q prime integers. On the exam, guys, don't neglect that. On the quiz I had you do, everybody except one of you lost 1 point. So I was feeling lenient. At first I subtracted 2 or 3 points, but I said, that's even too bastardly for me. But tell me what these q's are. They're not irrational numbers. They're not fractions. They're integers, in fact. That's very important. So from here, then, if I add here, I get that A plus A prime minus quantity B plus B prime is n times q plus q prime. And there's a multiple of n sitting there. That implies that A plus A prime is congruent to B plus B. Multiple of n. How's that? What's the proof? Know the definitions very, very well. To be congruent, for two numbers to be congruent mod n, means the difference is a multiple of n.
How about the one for the product where it's A times A prime is congruent to B times B prime?
And for that one, you would use the other method. So this also implies over here that A would look like some QAN plus R, B would be QBN with the same R. And likewise, A prime is QA prime N plus R prime and B prime is QB prime N plus R prime. Okay? Same remainders. And again, the Q's and R's are integers here. So from here, this would imply that AB becomes QA QB N squared plus QAR plus, QBR times N plus R prime. And likewise, AB prime would be QA prime, QB prime, N squared, plus QA prime R prime, Sorry, QA. Yeah, I guess I'm right. Plus QB prime R times N plus R prime. Now subtract here, over here, you get AB minus A prime B prime is a multiple of N, because these guys in fact cancel away. And that doesn't. Time for one more question. Yeah.
Is that what we want to prove?
Hmm?
I don't know if that's what we want to prove. That shows that AB is congruent to A prime B prime. But I thought the theorem was that A prime is congruent to B prime. It's very similar, but like.
Oh, that's true. Yeah. Damn it, okay.
Yeah.
Yeah, it's I'm multiplied wrong. You should be. Oh my gosh, pain in the butt here. A prime, B prime. Yeah, yes, you have to. I was wondering about these primes. A prime, R prime, A. Yeah, this is bullshit. Yeah, whatever. This is true here. Yeah, not worse. Sorry about that, I got my A's and B's mixed up. The proof is just the same thing, it's very easy. I mean, don't try to photograph it or memorize it that way, understand what's going on. So you just multiply things this way. If I go this way here, I pick up a remainder of R prime. But this way, I pick up the same remainder. The rest are multiples of n, and so the R prime subtracts away, and I'm left with it. Okay, we're out of time. I'm done. See you guys on Friday. Oh, fix it yourself. Take care.